So let us see some code on bitwise operations, and we'll be using the memory access methods.c file, on which we saw the two methods for memory access. So previously we had been using the struct padding.c, so I have just changed struct padding.c into memory access methods.c here in the makefile, because right now I need this file to be included in my project. So I've done that, and then let's bring it here. So this is my file now. So we were working on the SysTick load register, so we will continue working on that. And let's comment this out, or let's so by default the value of the load register has to be 0. So let's zero out all the values. 0x0 means we zero out all the values. So if it's a 32-bit value anyway, so if you just write 0x0, it is going to zero out all the values, all 32 bits. Now what we'll do is, let's open up the document. It's the programmer's manual, and we have the SysTick load value register here. So this register only sets the reload value count for the SysTick, but we will be using this register to check our bitwise operations, just so that just for the purpose of this demo. This will, setting these bits and clearing these bits won't do anything to the operation of the controller, but we will see how it is done. In the slides we saw a different set of registers being manipulated on, but here we will just use this register, but the concept is the same everywhere. So if you understand this, you should be able to work on any register, any peripheral register, or any system control register, anything for that matter. So having said that, let's proceed. So we know that if we are loading the base value with 0, in fact this value is 0 by default, but let us be completely sure and load a 0 here, so that the registers are indeed 0. And what we'll do is, as a first exercise, we are going to set the bit number 3, that is the 4th bit here. Okay. So from what we learned, what we are going to do is, so let's declare a variable, say uint32 underscore. So we are declaring a 32-bit value only. So we name it set 4th bit. Okay. So this is the name of the variable, and then and mind it, generally it's not a convention, but generally what we do is we have this set in caps. It's not something that you must do, but that's generally how it is done. We just do 0x1 or 1, whatever it is, 0x1, and then move it to 3 positions to the left. Okay, so set 4th bit. So when we step through this, we will see how it is, what this bit looks like, as we also discussed in the slide. So this is the set 4th bit. Now we will set the bit in the register. So what we need to do is, again, SysTick base load, whatever comes here, exactly like we saw in the on the slides, and then we just make it equal to set 4th bit. That's all. Now let us put this on debug and see what happens. We had the memory setup. Yes, we had the memory setup. So this is the memory location that is for the load register, and let's single step. So we single step through, and let's check the value. So the value 1 is currently 0 because the basic the reset value is 0, but nevertheless we are zeroing out all the bits again. And then let's see what set fourth bit has come to. So set fourth bit is 8 now, okay, because this 1 has been shifted by 3 bits. So it's a 32-bit value and the value is 8 now. Okay, now we will OR that value into this register. So what is right now the register looks like this. So now let's step one further, and as you can see it has become 0x8 and the rest are zeros. So the OR operation has worked and that register value has been changed to, so that particular bit has been set to 1, that is this bit has been set to 1 only. We have left alone the rest of the register. Now if you want to be completely sure that no other bit has changed, let us do F0. Okay, so we are loading the value F0 here so that you are convinced that really no other value has changed. We have not touched anything else. So let us do that again. So let's view the memory. So let's do a hex view. So all the values are zeros. Let's step through. So value 1 is 0 first, then set 4 bit becomes 8, and then as you can see now the value is 0 F0 and all the values go down like this. Okay, so and all are 0. So this is the initial value of the register. So it is F here. So the first these 4 bits are ones, that is these are all zeros and these are all ones, so that is why it is F0. So this is ones and zeros, and we have to set this bit. Suppose this is the initial state of the register. So when we go one more, we see it has become F8. Okay, so F8 would mean that this bit is set. So this is hex F and 1000, so it becomes F8. So thus we see that we have not touched anything else, we just changed that particular bit. And it's like if you want to get that value into a register, we see that it is make it F8 has come into this register. So this is the first step, that is where we just change an individual bit. So what we have done is, so this could be any number. So wherever you want the value to go, for example, if you wanted to set this one 21, so we could have gone there and set it. So that is the first one. Second one we saw was we had to zero in some values here. We had to zero out some values here first, and then we had to set these individual bits to something like 0 1 0 1. So we'll do it here. We'll do it here. So in this case, let us assume that those 8 bits are these 1 2 3 4 5 6 7 8. So say from bit number 16 we have to do that here. Whatever we have here, from here we have to set these bits to 0 1 0 1 0 1 0 1. And if the default value is 0, then we could just OR it with that number shifted by 16 left shifted by 16 bits. But to make it more interesting, we are going to fill this register up with all Fs, so that you know that. So let's fill up this register with all Fs, so or at least 24 bits with Fs. Okay, so F F F F F F. So all the registers are going to be filled with Fs. Now we have to, as per our requirement, we have to fill this with the bit pattern of 0 1 0 1 0 1 0 1, right? This is what we need to do. So we can do this like we saw in the slide. So this part is going to change now. So it will not be set fourth bit here. Let's say we say clear bits. Okay, let's stop the debug here. So clear bits. So when you do clear bits, as you can see here, we have to clear 8 bits, 0 1 0 1 0 1, or these are 8 bit locations. So what you can do is you can either do FF, which are 8 bits, or you can do 0 B 1 1 1 1 1 1 1. So it's clear to you that you want to clear those 8 bits. Okay, and of course you have to move it left by 16 bits because this is the field we are going to clear. We don't intend to touch any of this. Okay, we only clear that and we set our values whatever we want to. So say we move it left by 16 bits. So that's the first part. Okay. Now we could either have the complement being done here, or we could do it in the next step. So what we do is so when you have to clear, the technique is and equal to and then do a ones complement here. So what this does is it clears only those fields. Okay, after the clearing happens, we have to actually fill the bit pattern. So we can do int32 underscore t bit pattern equals 0b and then 0 1 0 1 0 1 0 1, and then say we have to move it 16 positions, of course, and then we can OR it. So same thing here. So we copy up to here and we OR it with a bit pattern. Okay, this should do the trick. So let's compile the code and see if this works. Okay, so we are getting some errors. So set 4th bit. Where is it? Oh, I'm so sorry. I didn't change this part. You see this? It's not set 4th bit. It's clear bits here. So then this should work. Let's compile it again. Okay, it's compiled. Now let's single step. So we get into this and this value 1 is 0. We know that. Okay, now let's see what the value of the system base is. So let's go to memory and 1 4. So we have FF and 0 0 on the top two are 0 0, and we don't bother because as you can see in this particular register, these are unused, these are reserved actually, so we didn't bother to. So all are Fs now, so all are ones. So if you come back here, this entire 24 bits are filled with ones. That is what this signifies. Now we have to clear the top 8 bits or the top byte. Okay, so let's step once. Okay, one. So we have just, so what is clear bits now? Clear bits if we if you see the value here, if you make it into a hex number format, hex, you see that the FF, this is FF actually. So this FF has come all the way up here to the top because we rotated it and brought it here actually. You can view it in binary. So let's see. This is the binary value. Okay. So 1 1 1 1 1 1 1 1 is the top value. So if you count this, it will be 24 bits, and this value has come on top. All right. So now we have to clear that. So keep an eye here. That is those top 8 bits we have to clear before we write into them. So one more step, and what we see here is, if you check the bit pattern here, one F has reduced here. It was all F's, now one F has reduced. That is, the top bits have been cleared up. Now once the top bits have been cleared up here, okay, we can write the bit pattern of 0 1 0 1 0 1 0 1. Okay. So this one is still the clear bits is what we saw here. So we are not seeing that value here, but system base, if we can check out system base and the value here, that is a load value, that will also show the same value to you. So you can check the value here, and this is the value that you see. Okay, that's a load value. Now this one 0xFFFF, okay, because the top part is all gone now, it's all 0, so it's not showing it here. So it's FFFF for the bottom value. So we have to now change the top value here, that is, we have to make it 0 1 0 1 0 1 0 1. So let's step once. Now the bit pattern again has to be moved by 16 bits. So let's see what the bit pattern is. Let's move this out. Number format, hex. So bit pattern is 5 5 with all zeros. So this is, so if you see 0 1 0 1 0 1 0 1 is actually 5 5. Okay, so this is 5 5, and then now what we do is we write that bit pattern into the register. So what we have is FFFF 5 5. See that? So this is, so this one has got 5 5 in it now. 5 5. Okay, 0 1 1 0 1 is 5, 1 0 1 is 5. So 0 1 0 1 0 1 0 1. So this is 5 5. Okay. So this is how you clear a bit field and write into that bit field. So now for this one, the next one, that is the checking for if a bit pattern has appeared in a register. So now we have, let's stop the debug. So now we have managed to clear a field and set whatever pattern we want, and this is something that you are going to need over and over and over again, okay, in your whenever you are writing embedded applications. So now let's see this. Let's so this is 0 1 0 1 0 1 0 1. So let us check bit number 23. So what we'll try to do here is we'll try to create the while loop and change this bit in the IDE and see if we can create that scenario where get stuck in the while loop and then it comes out. Okay, so let's do that. So bit number 20, so we are checking, say, bit number 23. So to check bit number 23, we know that we have to, so again do UI nt 32 underscore t and then say bit 23 check, okay, equal to 0x1, and then since it's bit 23, as you can see here, we have to move this value by, shift this value by 23, left shift 23. So this is the bit, so we are checking that particular bit. Now let us copy the while from here itself to save some time. So we do a while, and this one is going to be completely different, of course. So it is this load. So we are checking on the load value, right? This load, Control V, and bit 23 check. Okay, so we are checking if the bit is set or not. Now what is going to happen here is that this bit is anyway right now it is cleared, the 23rd bit, because it is 0 1, right? So it is a 0. So we'll see that when we put it in debug and we single step through, we'll get stuck in the while loop. So let's see what happens. So all of this is okay, all of this is what we saw previously, so we are not going through them again. And let's come to the while loop. Now when it goes to the while loop, as you can see, it is stuck in the while loop. It's not coming out. It is just stuck there. So let's do one thing. So we'll go to E014 and do a hex, and then so let's go to the memory browser now. So 0x E 000 E014, just enter. So this is the value 0x555555. Okay, so 55, okay, 5 is 0101, so 5 is this, so it is 5 is 0101. So if we make it 1101, so 1100 is, so this is 13, right? So 8 plus 4 plus 1, this is 13, and 13 is A is 10, B, C, D, A, B, C, D, right? So A is 10, B is 11, C is 12, D is 13. So we'll make this value to be, instead of 5 5, we'll make this value D5. Okay, so if we make it D5, it means that okay, so we make it D5, so we set that bit. Now so once we have set the bit, okay, so D5 is set. Now let's try to single step, and you can see it has come to return. So this means that once we change this bit, the while loop has figured out that that particular bit has been set, and it comes out of that. So what we did is we set the bit here, and once we set the bit here, the while loop knew that it is 1, so it is a non-zero value, so it came out, because while it was 0, this means while it is 0, it keeps at this looping here, and then once the value becomes 1, it comes out. So it will not be single stepping for you. It is going to be, you are going to have this in the code. So this code is going to run, and within the code all of this is going to happen. You may not realize it, but this is how it goes. So once we change this value, it comes out of the while loop and it goes out and continues executing the program. So this is a demo one. So this was a demo on all the bitwise operators. Now you realize that this is not a C foundation course. This is the C that is only required for the microcontroller lessons that we are going to go through for this particular course. This is not a foundation course, so you should have some at least intermediate knowledge of C and C pointers, because that is something that I'm not teaching here. Now let us briefly see how pointer arithmetic works. So I've created a new file called pointerarithmetic.c, which is just a copy of the memory access methods.c file, but I have deleted the body of the main function. So we'll see that. So in the makefile, let us change this to pointer arithmetic.c, and let's open that file. So it's exactly the same file. All I've done is I've just deleted the body of the main, whatever we had, because now we are going to see some aspects of pointers. This is how the conventional pointers actually work. So we are not accessing any register in this particular demo. We'll just show how the pointers advance when we increment the pointers. Mostly. So we do uint 32 underscore t, and then say it is a word. So word equals to, say we give some value. So and then we declare a pointer. So just call it a pointer, say 32t star pointer, and then we will do equal to ampersand word. So this is something that you already know. So now we are going to increment the pointer by, say, 1. So we do pointer plus. That's all. So, and we see what the value of the pointer is after we cross this particular line. So let's compile this. So we initialize the PLL as usual, and then we fill word with the value of 4567, which we see here, and then we step once again, and the pointer has the address of where the word is. So the address is 2, so we have 2000003F4. So this is the address of this particular pointer variable, and this is in the stack area. This is in the stack, and let's increment the pointer. So from 2000003F4 it became 3F8, because this is a word pointer. When we do a pointer plus, the value increases by 4. Now let us declare a half word pointer, and see how what the behavior is. So this is a so let's try to do uint 16t star pointer. Now we'll see a type mismatch warning here. That's okay. Let's see what we get. Okay, so 0 error 1 warning. See, it says incompatible pointer type. So what we need to do is we need to typecast this here as well. That is, we need to do uint 16t 16 underscore t and then ampersand word. So now this is going to work. So it's a 16-bit pointer now. uint 16t star, of course, and then ampersand word. Okay. So even though this is a 32-bit value, we have a pointer to that 32-bit value, which is a pointer to 16-bit. Okay, so let's see what happens. Okay, so this compiles peacefully. So this is still a 32-bit value. Word is still a 32-bit value, but we have created a pointer which is a 16-bit pointer to that value. So let's see what happens. So we have the value 4567, it's a 32-bit value. Then let's see, the pointer is 3f4. Okay, 200003f4. Then let's increment the pointer, and we see instead of 8 that we saw last time, it is 3f6. Okay. So this essentially means that if this is a word value, so 4567, whatever word you have, so if this is a 32-bit value here, sorry about the crooked drawing, it's a 32-bit value here. Say the pointer was pointing here first. In the previous case, the pointer skipped the entire value and it came here. That is, it jumped by 4 bytes. Now in this case, when we declare a 16-bit pointer, it is still not out of the value. It is pointing somewhere in the middle of the value here. Okay, so it is pointing somewhere here. One more jump, it is going to come out. So we will need such pointers. In fact, this could have been anything. This could have been a half word. It could have been a byte and so on. This could have been anything. Okay, but what type of pointer you declare on that particular value could be anything. So this could be a 8-bit value, but you declare a 32-bit pointer. So let's try doing that. So say this is an 8-bit value. So uint 8 underscore t. So we have to, of course, reduce the size of this, otherwise we'll have a problem. So this is a 8-bit value, but then we can declare anything 16-bit or 32-bit pointer to this particular value. No harm. Depends on your use. For example, let's compile this and see. Compile and put it on debug. Okay, so sorry about that. We have to typecast this as well. Yeah, so save this and debug. Now this is also permissible. So we'll see that. Let's minimize this. It goes down here like this. It's 67 here. The value is 67. It is saying it is C because just it's thinking it's ASCII. Just don't bother about it. So we have just 67 here, and let's see what the pointer is not yet been assigned. So when we go one step, 200000003f7. Okay, so this is the value we have here. Okay, now let's increase the pointer. Now, even though this is an 8-bit value, so 8-bit value at 2000003f7, when we increment the pointer, it increments by 4. So if you see, you just have the 8-bit value here, and the pointer was first pointing to this value, and then when we increment it, it comes here. So it skips the value by 3 and it comes here. So it is up to you how you want to manipulate with the pointers. So this is another way. if you make this value as, say, let's make it a 8-bit value now. So it is a pointer to 8 bits. So it's a pointer to 8 bits. So recompile. Now let's step through and see what happens. So this is 67. It gets the pointer value is 3f7, and then when you increase the pointer here, it becomes 3f8 because it's a byte pointer. So it just goes up by one memory location. So I hope you are able to understand the concept of pointers. Now let's do something else. Let's increase the pointer by a higher value. So let's say we declare this as a 16 half word pointer. So it's a half word pointer here, and instead of doing a pointer plus plus, let us do pointer plus equal to, say, 4 or any number. Okay, when we do pointer plus equal to 4, basically what happens is we are incrementing the pointer 4 times. Okay, but this is a word, so let's see what happens here. Okay, so let's redo the let's go through it again. So the pointer value is now 3f7 to 2000003f7, and then we are incrementing it by 4. So what should be the value? Make a guess. Let's go one step further and see what we get. So we got from 3f7 we got 3ff. Okay, f is 15, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it incremented by 8 places when we gave a plus equal to 4, because at every increment it is jumping 2 places, because this is a half word pointer. If this were a word pointer, then it would jump 32 bytes, or it would jump 32 places. So I hope you are understanding what is happening here. So pointer arithmetic is a bit confusing, but this is how it works. So when you designate a variable as a pointer, C or the compiler looks at it in a different way. If it were word, suppose word, if you do word plus 4, it will be 67 plus 4. So it will be 71. But if it's a pointer, then the style of incrementing the values is going to be entirely different. And this is something we will be seeing in our course. That is, we will be using this pointer increment and checking, checking certain pointer values, and then filling up memory places, filling up memory areas, and so on and so forth. Okay, so we'll do all that, and for that you need this particular, need to understand this concept. So I hope you understood how pointer manipulation happens, that is, pointer arithmetic works. If you do a minus now, minus would put the pointer in a, if this is what do you say, if this is in the beginning of the stack, if you do a minus, it will probably go into the data section and so on. So it is not advisable to subtract a pointer until you are absolutely sure about it. But then let's do a -2 and see what happens. So we know that it is in the pointer region. So let's do pointer minus minus. Pointer not -2, minus minus, and see where the pointer goes now. Let's recompile. And let's step through. So plus 4, it went to FF. Now let's see where it goes. See, it went to FD. So it reduced by 2 again. So you can move the pointer backwards also, but you have to be very careful where you are moving the pointer. Yes, pointers are could be extremely dangerous if you are not handling them properly. So this ends the demo on pointer arithmetic.